So firstly, thanks to Effectory for hosting this, and thanks to the user group for inserting this rather last-minute talk. By last minute, I mean I discovered that I was going to do it at about 4 p.m. today while we were in our office in The Hague. So my name is James Nugent. I work for a company called Event Store, among other things. We build a database for event sourcing, which is why we're going to talk about this. Prior to that, I've worked at a bunch of tech companies, Joyent, HashiCorp, Boundary, Jet.com, all kinds of stuff, applying some of these principles. And so I'm aware that, so I've given this, I did not write this talk between 4 p.m. and now. This is a talk I've given before. And I realized that it has a rather unfortunate title for the Netherlands, because someone informed me that SOA has a different meaning here. And then I checked it on Google to confirm that other meaning. So unfortunately, I did not rewrite it, so sorry about that. The other interesting point is that my laptop didn't really work with the setup here, so I have the notes on here and the slides on here, so it might be a little bit slightly disjointed. So I'm going to try and do a whirlwind tour of all of these things, of service-oriented architecture and how event sourcing fits into that, and then how another pattern called CQRS, or Command-Query Responsibility Segregation, fits into that as well. I'm not really going to look at much code, although there are a few snippets throughout the slides. So before we spend time looking at event sourcing or CQRS, I'm going to spend a bit of time putting them in context. And one of the mistakes that was made early on in event source systems, so 2006-07 kind of time, is when this pattern sort of emerged as being a good idea. One of the big mistakes that people made was trying to apply it everywhere in a system. So every aspect of a system would be event sourced, or every component would be event sourced, or sometimes there would just be one component and it would be event sourced, covering everything. So I want to talk about SOA first, SOA, service-oriented architecture. I don't know how old people are here in general, but when SOA was first talked about in the late 90s, I guess, early 2000s, this was one of the phrases that you'd find, like, this was the purpose of it, right? The aim of this architecture was to help align what IT were doing with what a business were doing, right? And the way it got adopted was companies that had tools that didn't do SOA would write articles in seatback magazines for major US airlines about how everybody should be adopting SOA. And then they should be adopting their tools. And naive CIOs and CTOs would sit in these planes flying around from place to place in the US. They'd read them and say, oh, everybody appears to be doing SOA. We'd better do that too. And that's what caused it to be adopted. And the problem is, if you look at what became of SOA over the first few years of its life, it's hard to see how it came back to this objective, right? So let's go back for a while to, was anybody here building systems in, advanced COM or something like that in the late 90s? A couple of people, okay, cool. So let's think, a stereotypical architecture of a system from the 1990s, right? We had a client, usually a MFC app, or occasionally something, maybe Java or something like that, talking to a database. And the database had all of the logic in it, and lots of clients, like everybody's terminal, would connect to the database, and that's where all the work would be done. And people realized over time this doesn't really scale very well, right? As the number of users increases, this doesn't actually work that well. And if you want to expose it to the internet, then this really doesn't work very well. So what ended up happening was we added an extra layer in, right? We called it a business logic layer. And this would run on an application server, abstract the database away, and the clients, which could now be some kind of web app, or maybe by this time probably a WinForms app or something like that, would talk to the business logic layer, and the business logic layer would talk to the database. And then this is kind of the state of the art for the three-tier system was kind of the state of the art in the early 2000s when SOA became a thing. So having been through this transition, what people did was say, well, clearly the thing we're going to do here to do SOA is add another layer called services, right? So as services are just going to sit in front of the business logic layer, usually do exactly the same thing as them, and then just proxy calls down one layer extra. So now you have a bunch of extra XML, because it was all XML then, running through your system, and nothing really improved. So if we look at this, it's kind of hard to see, how does adding this extra layer here help achieve alignment between what your business wants and what IT or development wants to do? So the problem with this term service is, you can look at it like this and say, well, obviously we just add an extra service layer and there's no problem. But the problem is, what is a service? And to be useful, we have to have a common definition of service. And service is like the most overloaded term in the industry. And apparently is even worse for non-native English speakers, because it also has another meaning which is completely disjoint in English from the meaning of the word as we're going to use it in technology. So, in particular, in the US, you go to a restaurant and you have a server who serves you or gives service to you. And that doesn't really help us for achieving IT business alignment, because it has nothing to do with it. So let's see if we can do a better, see if we can try and dig into what service actually means so that it can be useful in achieving IT business alignment. So in the Microsoft space, the way that people started with SOA was this crazy-ass keynote by this guy called Don Box at PDC in about, actually, so Dave there used to work at Microsoft at this point, I think. Don Box, a distinguished engineer at Microsoft, or maybe a tech fellow at Microsoft at this point, gave a keynote about how SOA was going to work and defined these 4 principles. He actually gave it, sat in a bathtub on stage, like actual roll-top bath filled with water, gave his keynote in the bath. Cool. Yeah, and it was certainly interesting. But he basically defined these 4 tenets of what it means for an architecture to be service-oriented. And if we go down, they all sound like obviously good and actually sort of relatively self-evident things, right? So services should be autonomous, and they should have boundaries that are explicit, and we don't want to be sharing binary artifacts among them, but instead contracts, and that we don't want to hard code the way these services talk to each other. We want some kind of policy that controls that. And these are all obviously good things if you just think through them. But if you go back and think how the WCF or the Java equivalent of WCF, whatever that was, like adding a service layer helped achieve these, and think them through for a minute, well, it does the last 2 okay. If you have a WCF service, for example, sure, you share like a contract and you don't necessarily share a DLL between them. And actually the policy stuff is really good. It has lots of configuration points about how a service talks, the transport for it, the security around it. That stuff is great, but the first 2 are a problem. If I have WCF service A and WCF service B, and as part of serving a client, service A calls service B, can we say that service A is autonomous? And the answer is clearly no, because if B is down, A can't serve its clients anymore, so A has a strict dependency on B. And the other problem is, although there's a clear boundary at the front door, there's a clear contract at the front door of a service, there's nothing that really says what it can do from there. So it's kind of like having a front door but no sort of walls or roof or anything. So what we're looking for really is a definition of service and service-oriented architecture that uses something different than inserting a layer of web service calls in our application architecture. And there we go. Cool. So this is the definition, for want of a better one, that I'm going to use throughout the rest of this talk. So a service, as I'm talking about it from service-oriented architecture's perspective, is going to be the technical authority for a specific business capability. It's kind of a broad statement, but let's think about what it means to be a specific business capability. So if you're going to be a technical authority, not a business capability, let's look at what it means to be a technical authority for something. So if you're going to be the technical authority for something, you have to be able to make decisions. So what that means is that all the data and the rules that you're using to make those decisions have to live within a service. Right? So if I have a bunch of reference data in a database and a service, some kind of application function that makes a decision based on that data. From a logical perspective, the data in the database and the logic in the function are part of the same service, because they're part of being a technical authority for a particular capability. And so the corollary of that is, once you've divided your business or your architecture up into services, there are no pieces left over. So it's not a layer in an architecture, it's something which encompasses every aspect of the architecture. So before we look at some examples of what might be services in this model, let's look at what are definitely not services in this model. So a service that only has functionality, only has logic in it, is not it's a function, it's not a service. Right? So if you have something that's stateless and just adds two numbers or calculates sales tax or something like that, it's not a service, it's a function. Whether you wrap it up in XML over RPC, or whether you call it via a WebSocket, or whatever, whether it's wrapped up in some kind of a React component or whatever the hell people want to do with them, logically, in an architectural sense, it's a function and not a service. And furthermore, a service that only has data and does CRUD operations on it, or writes or saves it or whatever, is also not a service, it's a database. Now, functions and databases are obviously part of software, and they're things that we have, but if we call them services, then the word service becomes meaningless, and we can't use it to refer to any sort of larger construct which is more meaningful. So if we go back to that article, if we go back, to the original definition that we had, and look at what we were doing commonly in those 90s, early 2000s, mid-2000s systems, what we weren't doing was building a service-oriented architecture. What we were doing was building systems of functions, calling other functions, calling other functions, calling databases, which is clearly not very efficient. There's a view of software published in a paper from 1996 by a French author called Philippe Cruchat, whose name I probably just butchered, sorry, for anybody French here, which specifies that what you can do is separate any software system into lots of different perspectives. So you can look at the same project from lots of different people's perspectives, or lots of different perspectives within, from logical perspectives. And the architecture of each of those doesn't need to be the same. So it separates things into a logical view, which is, where are the logical business boundaries of these components within a system? It separates it into a development view, so where does the code for each of these live? Which source code repository does it live in? Which Visual Studio project or solution does it live in? It separates it into a process view, so when this software is deployed, who's responsible for each aspect of the process to get a particular component of the system deployed? Who has to QA it, who has to press OK on the release process, something like that. And finally, it separates it into a physical view. So when you're running on physical servers or in a cloud, what's the deployment topology as opposed to the development topology, or the logical topology, or the process topology? Now, one of the things that's commonly been done recently is to couple all of these together. And if you couple all of these things together, what you get is microservices. Right? You get one repository that leads to one release process, that leads to one type of physical server running a particular process, or maybe one Kubernetes pod or something like that, which represents one logical function of the system. But that's not the way it has to be. You don't have to do that. You can instead tease these things apart and gain flexibility from being able to address each of these in a way that suits a particular organization. The paper is called the 4+1 architectural view model. The +1 is the fact that all of these things are bound together by use cases of a system. So you have a particular path through a system, and for that path, you should be able to identify this is the logical components involved, this is the where the code lives, all that kind of thing. And this is actually kind of useful to us, because if we take our other definition of service, the wrong way. I really dislike this clicker that I borrowed from Dave. No worries. The buttons are like, there's 3 buttons, firstly, and it's like the bottom one doesn't do anything. So many services, so what we're going to end up with, if we separate the logical, services live in the logical tier of our 4 views of architecture, right? These are the top level decomposition of our system into components. An application is more of a development or process or physical view, and it's kind of up to the company as to exactly where they fit. So what we can end up with is a single application that consists of components from lots of different services. So many services can have components deployed in the same application. One is a one is a lower level composition container, and the other is a logical grouping of things that go into an application. Oh, again, the wrong way. So what we often end up with is seeing services as being vertical slices and containing components throughout the traditional layers of a stack. So they're vertically cross-cutting instead of horizontally cross-cutting. So to use a, wrong way again, I'm just going to keep my finger on the down button and hope I don't move it again. We can, for example, see that if we were in an e-commerce situation, we might have a marketing component of user suggestions which has some UI associated with it and uses one particular strategy for the back end. But we could choose to use a completely different back end technology for the UI components in a different service relating to the product catalog. But all of these things would be deployed together. The UI would probably be deployed into some kind of website that's doing composition somewhere either on the server or at the client. This is not an accidental example because one of the original people that did SOA, sort of by fiat, and discovered a lot of these patterns was Amazon.com. The reason Amazon.com did SOA is not because they looked at the tenets of SOA or saw Don Box's keynote or anything like that. It's because Jeff Bezos sent an email to every senior manager at Amazon saying, you need to be doing service-oriented architecture within 6 weeks, and if you're not, you're fired. So within 6 weeks, they all figured out, well, what does SOA, how does it benefit us, what can we do with it, because otherwise we're fired. So probably different teams had different takes on it, all to say that they were able to do it. But if we, maybe I got rid of that slide, sorry, hold on. Okay, sorry, I cut a few things out to try and keep this down, I don't want to talk about that for a second. If you look at this page from Amazon.com from a few years ago, this is the domain-driven design book, which covers a lot of concepts about domain modeling. You can clearly see that different aspects of this have different ownership models, depending on which responsibility of the business or which capability of the business contributed the data. Right, we have some stuff that's very static. We have a picture, title, some reviews maybe. They're all clearly product catalog information. We have the particular price that's being extended to me. That's clearly not the product catalog because not everybody has the same price for every product. There's something else that knows for a particular product, this is the price that's extended to a particular user. And then down here, it tells me how quickly I can get it, and based on where it knows my shipping address is, my default shipping address, and whether or not the thing is in stock. This is clearly also not related to the product catalog, right? There's a shipping domain somewhere that's calculating if he orders it now, I can send this to this person within 5 hours and however many minutes. So what we end up seeing is that applications become a composition of components which live within different logical services. So our logical view of the architecture is completely different from the physical view or the development view of our architecture. And what we start ending up with then is composite applications, which and there's some choices to be made as to where they compose. But that's effectively the real principles to help you actually get to the point where service-oriented architecture can help with IT business alignment. So there's another statement of this, by the way, of the 4+1 architectural view model, and it's become, again, more popular recently as people have discovered it talking about microservices. And it's a law from a mathematician and computer programmer, computer scientist called Melvin Conway, who observed, I have a story about that in a second, but who observed that organizations building systems tend to build systems which exactly mirror the communication structures of the organization themselves. The best example of that is if you have 4 teams building a compiler, what you will have is a 4-pass compiler. Right? Everything will go through a stage developed by one team, because that's how the communication structures of the organization go. Services map very neatly onto that because business capabilities tend to have internal communication paths that are separate from the external communication paths in those organizations. Mel Conway this paper was published in 1968. Actually, I recently had dinner with him in Boston. He's still working and still alive and still working. He started at IBM the year that my father was born, which gives you an idea of how long he's been working on this kind of stuff. And still doing interesting research and publishing interesting papers, which is nice. So, what I want to talk about briefly next is a pattern called event sourcing. I'm not going to dwell too long on this because Chris is going to talk about it afterwards, but event sourcing, as it fits into an SOA, it's not a top-level architecture. Right? You can't take a business and say, we're going to do event sourcing here, and then start writing code. Right? There's some decomposition required because you only use event sourcing in particular areas of the system. So if we go back to our no, that one. If we go back here, we might choose to use event sourcing for user suggestions or for inventory, but not for other aspects. Right? You're going to apply it to some small, it's a pattern that should be used within a particular service. So, what is it? Has anybody here heard of event sourcing in the past? Cool, okay. So for those who haven't, I'm going to try and do a fairly basic introduction to it and try and keep it fairly quick because Chris is going to go into a lot more depth shortly. Who here uses an ORM for their system? Entity framework, NHibernate, still, anybody? Cool. What's the other one? Java, what's the main Java one? Hibernate, JPF, something like that. There's even one in Rust now called Diesel. So here's a question for you. If you have an ORM, who decides what transaction goes into your database? Is it the programmer? Is it the user? No, it's the ORM, right? The way an ORM works is it loads a row from a table or a few different rows. It puts them into an object model. It keeps a copy of the object model. It gives you another one back to mutate. And when you're done, you call save. And it compares the copy it kept and the copy that you gave it back, mutated, and works out, well, what SQL transaction do we need to run to get the database to match this object model? Is it always correct? Has anybody ever looked at the code base for NHibernate? Was that fun? There are a lot of code, right? NHibernate is tens of thousands of lines of code. You sure it's correct? And the answer is it's definitely not correct. Entity framework may be a bit more correct now, but that had its moments early on as well.
They have unit tests.
Sorry? They do have unit tests, yeah. I believe, does NHibernate even have tests? I don't know. Yeah. It probably does, okay, cool. Here's another question for you. Who here has an audit trail in their system? Cool. So if you have an audit trail in your system, if everyone that had an audit trail in their system can put their hand up again. Okay, keep your hand up if you can prove in a courtroom that your audit trail is correct. Cool. That's a very common response, right? So if you can't prove it's correct, what's the point in having it? Like, it's a lot of work for nothing, right? In particular, if you have an audit trail based on an ORM, then not only can you not prove it's correct, you probably also can't prove why. And in the kind of systems that require an audit trail because of regulation, that's a problem, or it can be. So the fundamental point of event sourcing is, or one of the fundamental points, or the original point, was to solve those two problems. Right? The reason it came about in the modern day, it's not a new pattern by any means. It was in use since if you look at like an IBM mainframe, the entire system works by event sourcing. But in the modern, since 2005-06 kind of time, the reason it came about was for financial transactions. We're building algorithmic trading systems and needed to be able to prove that what the system said it did is exactly what it did, because these things were playing with real money in the market, and they were very, very fast. And if you put something in the market that's playing with real money very fast, you can lose a lot of money very fast. And you need to be able to know, why did this happen? Who do you fire today? And how do you make your money back? Right? So the fundamental revelation of this was, not that, or that. It was that state changes in a system need to be an explicit part of a model. So an ORM makes them very implicit, right? You go and you take an object, you mutate it a bit, and then you say save, and your state changes whatever change was derived. But actually, if you're trying to model a system to say exactly what happened, what you should probably do is make these state changes an explicit part and name them. So instead of doing that, instead of doing what we do with an ORM and deriving state changes, instead we capture the state changes in an object or a business entity as a series of events. So events are things which state something that happened. And specifically, I don't know if Dutch has this, but specifically something that finished happening in the past. So French has le passé composé for expressing these things. So it's this thing that finished happening in the past. And that can lead to some awkward constructions, but here's some examples. So an event is an account was promoted to gold status. Another one is the application was submitted for approval, or the credit card check failed, the credit check failed. These are all things which have finished happening. They're facts about a system. And if you know all of the facts about the system, then you can use them in interesting ways to derive the state of a system. So let's look at an example. This is my favorite example because I used to work for a big e-commerce site, not Amazon. Everyone could imagine modeling a shopping cart in a relational database, right? So you'd have your cart, and you'd have some line items, an object model of them. You'd have the cart, you'd have some line items, you'd have some shipping information, and you can see how you'd map that onto a relational database, right? You'd have a cart table, and the cart would have customer ID, and then the cart would have a one-to-many relationship with the line items in there. And you probably have an item ID and a quantity for each line. And that's one way to look at it, right? This is a structural model of a shopping cart. It's not the only model, though. A different model would say what we're going to do is look at the events that caused a particular cart to get into a given state. So instead of saying, wrong way. Instead of mutating this table and say, we change the quantity of socks in my cart down from 5 to 3, and just updating this quantity field here, what we're instead going to do is keep a record of the events that led us to get to that state. So we're going to keep a record of, we created our cart, and then we added some shirts, and then we added some socks, and then we removed a shirt, and then we checked out. Are these two models equivalent? They're not, actually. So they look superficially equivalent, right? But there's a subtle difference, which is in this model, I know why I'm pointing it at the screen, it's not going to work any better there. In this model, we're mutating a static state, right? So if we remove an item, we're just updating the quantity and saying, well, now we have 1 instead of 2. In this model, we retain a complete history of exactly what happened at which point. We can rebuild this model by replaying all of these events and saying, well, if we see we added an item, we're going to go and put that in the table. If we remove an item, we're just going to update the quantity and set it to 1 minus. So we can use this to derive the structural model. And in fact, we'll see we can use this to derive any structural model, not just a table system. But actually, we've lost information in the other one. Because we've gone and mutated something, you can't recover all of the lost data, right? This added 2 and removed 1 is something that disappears in that model. Now, there are ways of doing temporal databases that don't do that. I'm not discounting those. They work in some places quite well. But they're a much more complex model than just retaining a list of what happened. So if we can create a structural model by replaying these events, then storing the structural model anywhere in our entire system is just an optimization. Right? Instead, we could persist the entire domain model just by keeping that list of events that happened. And it tends to be that mature industries have this as a foundational principle. And particular mature domain models already do this by default. Who has worked on accounting systems before? Or is anybody here an accountant? Okay, cool. Oh yeah, I forgot that. Accounting works like this naturally, right? You don't update the state of your bank account and say, set the value equals $50. You maintain a journal of all the transactions that got it there so you can verify it's correct. Also that you can go and run different transactional calculations over it to discover a different model based on the same transaction history. That's how fraud analysis works, for example. So I'm going to skip over most of the code here because we don't really have time for it, but in fact I'm going to skip over all the code here. There are plenty of examples of this online. There are some frameworks to help you do it as well. But so who here would consider themselves a functional programmer? F# programmers, anyone? Cool. So in functional terms, event sourcing is really simple. It's like a one-liner. It's the current state of an object is a left fold over the previous behaviors. So what does that mean? Where are we? Okay, I'm just going to wing it and see. Actually, so we can go further than that. We can project any structural model, right? So when we looked at it before, we were going to project back we were going to replay the events and build our structural model from the list of events. But actually, there's no reason in principle we can't also go and build a star schema for reporting. Right? It's common in enterprise systems to find that you throw away all the data that you need to go and build a reporting database, and then you rederive it from the crappy data you actually kept. If you keep all the events, you can use them to build lots of different views into the same data because you have a complete set of exactly what happened and why. It also solves the audit trail problem. If you need to be able to prove exactly what happened at a given point, write it to write once media, and suddenly you can't go and change what happened in a system. You can't have the situation where the operator goes in and changes the bet just before the winning horse comes in. A real system with a real story behind it, which can be talked about over beers later maybe. Okay, it also has a dramatic impact on testing. So who here tests their system? Cool, everybody, right? So who tests that their system does what it's supposed to do? He does, okay, cool. I have a different question though, and that's, cool, that everybody does that. Who also tests that their system does nothing it is not supposed to do? That's a much harder problem, right? You don't go and look at every database row after you run a unit test to prove that it hasn't changed. Event sourcing changes the nature of programming slightly, because you don't have side effects all over the place. It makes it a much more functional approach, and business logic becomes much more like pure functional programming. So let's look at some example tests with this. What every test becomes is, for an object, given the past behaviors of the object, so the events that have happened in the past, when we call this particular method or when we do this particular operation, then we get some other events out of it. And more importantly or as importantly as these are the events we get from it, that we don't get anything else. So if we decouple the downstream effects of a system, the effects from the decision to make the effects, we can test that the decision was correct by asserting that only the decisions that we wanted were made. And that makes the testing problem much simpler, because it isolates the testing to being testing the downstream effects of something separately from testing that the correct decisions for those downstream effects to happen were produced. I also had some code in here, but I'm going to ignore that too. These are actually, that's worth looking at. It's worth noting that several of these, a particular method doesn't have to correspond to one particular event. So in this particular case, a particular action or a use case of a system, we're going to record a complaint from the subject of a particular review. That can result in multiple different events being emitted which affect different services in a system. Right? We can say we're going to emit an event which is going to remove it from the remove a particular review from the internet, and we're also going to use that to kick off the arbitration process for determining whether or not a particular review is any good. That I'm going to kind of skip over testing for the most part for the rest of that. That leads us to a problem though. If all we have is a sequence of events, how do I run this really simple query? And if all I have is my million shopping carts, each of which is represented as a sequence of all the things that happen to those shopping carts, how do I find, and this is it's not something you'd likely want to do, I want to do it. How would I find all of the shopping carts where the user's name begins with a J? So what you do is you'd replay all of the events for every shopping cart, right, and then you filter them all. That's a really terrible way of doing it. It's very inefficient. In a relational database, this is a solved problem, right, because it's something that relational databases are really good at. On the other hand, if I want to determine the connectivity of graph-structured data, so I want to find the cycles in the list of products that people added and removed, so that I can identify clusters where people are looking at the same sort of products and substituting one for another, then I probably want some kind of graph database instead, because that's what they're really good at. You can't query event streams directly except for one particular type of query, which we'll talk about. We probably won't talk about, actually, but it exists. Temporal correlation queries. Querying event streams is really good for that. So the problem with querying is you can't query the event streams because it's really inefficient to replay them every time just to get the result of every query. So there's another pattern that you can use for this, which is called Command-Query Responsibility Segregation. It's an acronym that really rolls off the tongue, especially if you're not a native English speaker. So it was shortened down to CQRS in about 2006-07 kind of time frame. The problem with CQRS is if you look at where the keys are on the keyboard, for years and years, if you Googled for information about CQRS, it used to say, "Did you mean cars?" I had a major victory the other day when my iPhone auto-corrected the word cars to CQRS instead, which was like a full circle thing with this, like 15 years later or whatever. And CQRS is a pattern which gets a lot more attention than it deserves. It's not a complicated pattern. It doesn't imply anything except that we service reads in one way through one code path, and we service writes through a different code path. It doesn't say we have to service them from two data stores or anything like that. Who here reads from views in their SQL database but writes into tables which materialize those views? Right, it's a pretty common pattern. But that is effectively CQRS, right? You're servicing reads from a view specifically designed for the read, and you're servicing writes through a table model which is optimized for writing. And actually, we can't service every type of query that we want via one model, right? A SQL Server database or a graph database or Cassandra or DynamoDB, they can never service every type of request that you're going to want to do. So you're always going to want other data stores that have different views of the same data in them. And the common example is a star schema from something like Redshift or a data warehouse in some kind of form. And the great news is, if you do event sourcing, then what we can do is apply the left fold that we used to apply to get the state of a particular object to derive read models. And you can derive lots of them from the same events. So what we can do is we can take the transaction log of all the events that have happened in our system and play them into different sources through different functions to get the benefits of each one of these specialized read models in the particular area that's going to be best at. So we could have a document database for serving our UI, a graph database for cluster analysis, and a star schema for arbitrary reporting. And the problem with that is we need to put all this stuff together, right? We have to orchestrate it. So the common way to do that, if you think about the view around a system, is we'd have a domain model which is now producing events. And we'd write the events into an event store, and we'd also write them out to a queue, and the queue would read all the messages and run the fold function and write into a SQL table, and then our client can query through a thin read layer that doesn't have to have an ORM, right? It could just be like linked to SQL or even just like select star from whatever to make its reads. There's a slight problem with this, which is what happens if you want to drop your projection. So you decide, oh, I now need this new view of the data. I need this extra table. And what you want to be able to do is go back to the beginning of time, replay everything from the beginning of time, and construct this new model with all of the pre-existing data in it. So one way that you could do this is have two-phase commit between whatever queue you're feeding into your denormalizers and your event store. That is one way to do it. So two-phase commit, everyone's familiar with, like a DTC or something like that. Who's operated the Microsoft DTC at scale? Anyone have fun with that? Does anybody ever wake up to the emails that says a transaction is in doubt on your coordinated transaction system? The state of your system is unknown. So the way to solve two-phase commit. So the problem with two-phase commit, right, is a system that says, okay, let's say your database 1 and your database 2. So I'm going to say, I want to write this. Prepare this write. Okay, you say fine. I say to this other guy, prepare this write. He says, okay. And then I say, okay, well, we know these two can do the write. So now I'm going to say, okay, you commit and you commit. So the problem comes in the last phase, where if this database is committed but this one hasn't, then we don't know what the state of that system is, right? He could have received the commit message and then gone offline having done the work, or maybe the message got lost on the way, so now they're in an inconsistent state. So the solution to this is a different protocol called three-phase commit. It's actually not the solution to it, because all you do is defer the problem. So I once worked on a production system where we released a version of the software. Yeah, a little bit over, but this one's worth a slight diversion. We released a version of the software overnight with one minor bug fix. The next morning, and it was a tiny bug fix, like a typo in the UI. The next morning, every single operation in the system had 50% extra latency on it. Every single operation. And people spent days and days going through every aspect of the system trying to work out why it was slower. Because now transactions were timing out. And no one could figure out why. So then we deployed the old version with the typo again, and it was still 50% slower. Okay, so it was no longer the software, it must be the environment, right? So started talking to the admins and was like, well, what else happened around this time? He said, well, I got an email the other day saying your transaction is in doubt because of two-phase commit. One way you can fix this is to go and check the box that says enable three-phase commit. So I used the outage time during the upgrade to go and do that. So now, instead of prepare, prepare, commit, commit, every transaction is prepare, prepare, acknowledge, acknowledge, commit, commit, or 50% more round trips around the network. So, of course, they still fail at the end. So, well, now there's more points they can fail, so it's even worse. So that doesn't solve it. The solution here is to not have two separate things that you have to commit to at once. Instead, what you need to do is use an event store that you can write through and subscribe to. So you can write events into it and have subscribers hung off the back of it that will say, you know, when something gets written, this is going to get notified about it. And that way, if I want to throw all this away, what I can do is say, I know events, up to events from time 0. And then they'll get notified about everything from the beginning of time. Or I want to know about events from 30 minutes ago because I just restarted, and then it can just replay events from 30 minutes ago. So that's how you put it together, and that's what a stereotypical CQRS system ends up looking like. There is a problem with this, right? If you're not doing everything transactionally anymore, you have to deal with this thing called eventual consistency, right? If every database isn't being updated synchronously with each other, then it can be the case that this database is out of sync with the facts in this database. And I don't really have time to talk about how you solve that, sorry. It can be solved in almost every case. There are some strategies for it. I'll put these slides up, and then these are some ways. So as a quick summary before I hand over to Chris, event sourcing and CQRS, they're patterns to be used in the small, inside a service. They're not top-level architectures. They're tactical patterns, not strategic ones. Event sourcing as a pattern stores the state of business entities. Instead of storing the particular state at a given point in time, it stores a history of all the decisions that were made to get to that point. And then, in order to be able to query those streams, you need to apply this other pattern called Command-Query Responsibility Segregation to take those event streams and denormalize them into models that you can then query in whatever way you find optimal. So I realize I ran quite a bit over. So at this point, I will not do questions right now, but I will be around for at least these 2 cans of beer's time, and can have questions afterwards. So at this point, I guess we'll hand over to Chris, who has a much deeper dive into event sourcing specifically. So thanks for listening, and actually, I guess, since Chris is... thank you.